Yeah, thank you very much. And I guess I'm afraid you're wrong, but okay, so I'm going to speak about a joint work with Ben Antio and Achim Krause, and our goal, I mean, I guess the general goal of myself in the last couple of years was to compute algebraic K-theory. Algebraic K-theory groups of certain rings. And I guess we've heard like Christian just talk about a very impressive example of such a computation, and I will today talk about another example. And I mean, let me just say, I mean, I guess we haven't any, I guess Julia has explained to us roughly what algebraic K-theory is. Let me just say, like, I mean, these groups, as most of you know, were defined by Quillen, and I mean, Christian just had Quillen's computation on the board. Let me just recall it again. That Quillen, after defining K groups, the first thing he did was he computed algebraic K-theory of Z mod P. P is going to be a fixed prime throughout, and what is defined? He finds that these groups are given by the integers in degree 0. Then you have Z mod P to the I minus 1 in degree 2I minus 1 and 0 else. And what I want you to note here is that, I mean, in particular, we see that these groups are 0 in positive even degrees. So this kind of even vanishing behavior we have. And then, I guess, after this first initial computation, immediately a question came up. Namely, what about Z mod P to the n? Rings of this form. And that's what my talk is about. And let me just say, I mean, actually very little is known or was known about that. And so the only thing known is for, I mean, it's actually known in degrees star less or equal to p minus 2 by work of Algebraic, based on the earlier work of Prism. And I guess theoretically, in the literature, there was a little bit more, but that was wrong. I mean, specifically for p equals 2, you see this means it's literally only known in degree 0, 1, and 2, and there were some results in degree 3, but I think they're wrong. Okay, so anyway, so let me try to roughly tell you what was known, like kind of this only known thing. And I want to do this by contrasting it with another example. Namely the function field case. The function field analog of that ring would be fpx mod x to the n. And K-theory of this guy is actually completely known. Completely known by famous work of Hessel-Holt and Madsen. And let me maybe tell you a little bit about these two cases. So I put fpx mod x to the n here, and here I put z mod p to the n. Well, I guess first thing is k0 is the integers. Okay, that's not hard, and the same is true here. Then what about positive degrees? So the first thing you can prove by soft argument is that in positive degrees, this K star is finite torsion. The finite, I guess it's finite. So it's a finite group. In particular, it's a torsion group. So, and the same kind of soft argument actually shows you that this is also a finite group.
What's the soft argument?
I mean, for example, a homology argument, without calculating the circular style argument, you can prove this. I guess by soft argument, yeah, I think I adopted this term from Ben, who uses it like all over the place for basically everything. I think it's kind of the opposite of what Christian does. Like, you don't calculate with any spectral sequence or something, you make a sort of conceptual style argument. What?
It's when other people.
Yeah, I don't think this can be defined in a way which doesn't insult anyone. Okay, so next thing is that, I mean, of course, course, once I know it's a finite group, I can sort of decompose it into primes and compute the primary components. And the first thing you can do is you can invert P. Invert P, and then you see actually that this is isomorphic to K-theory of Z mod P. And I guess since I say it in positive degrees, this has already P invertible, so I don't have to invert P here again. So that's kind of Gabor rigidity or other arguments of this sort. And the same argument shows that this is also true here. So when I say this is only known for star less or equal to P minus 2, I'm specifically talking about the P primary part. Everything else is completely known. And now what about the P primary part? So note one thing, of course, this immediately also implies this even vanishing here for the part away from P. And now the point is that actually for, in this case, and I'm writing actually even degrees as 2i minus 2 for a specific reason, so don't ask me about this now. I just don't want to get confused with indices. That's why I'm writing even numbers as 2i minus 2. And so the P infinity torsion, so the P primary part is actually 0. So this K-theory is completely 0 in all positive even degrees. And here on the right-hand side, I guess I sort of have to line up here. It turns out that the same is true as long as star is small enough. So for I less than P. But then it's false in general because what unlike Nikolaus shows as the last thing is that K2P minus 2 of Z mod P to the n is actually isomorphic to Z mod P. So it's definitely not concentrated in odd degrees.
So sorry, this is for n greater or equal than 2, right?
Yes. I guess you're right, yeah. I guess, yeah, let's say somewhere n greater equal to 2. Yes. Okay, so this is kind of where this fails. And finally, one last thing. I mean, I guess these groups are completely known, but let me not sort of talk about what they are. They can be expressed in terms of so-called big bit vectors. But let me just give you one statement that one can prove, namely that the order of this group 2i minus 1 and P inverted, that this is actually given by P to the I times n minus 1. It's a finite group and this is the order. And it turns out there's an analog on this side, which is we can't say what the order of this group is, but we can say something about the order, the quotient of the order. So if I take 2i minus 1 P infinity and quotient it by the order of 2i minus 2 P infinity, then I get a formula that this is exactly the right same term, n minus 1. And note, I mean, of course, it's generalized, this statement here. If I know that the even ones are 0, then I could also like sneak in the order of the 0 group here. And okay, so this is, so you see actually much more is known than what I said here, that it's only known in these cases.
What does that depend on?
What does that depend on?
Who proved it?
Nikolaus. Like everything basically, but this you can see by an argument basically due to Brun. This is kind of a filtration argument. It's kind of once you know it's a finite group, you make a specific filtration and then it's a sort of multiplicative Euler characteristic argument. I mean, I guess out of our work there will also drop a new proof of this and a drastic generalization, but somehow, yeah. This is what was known. And now here's what we prove. So the first thing is that we show actually that in large degrees, we again on the right hand side have even vanishing. So we have that K2i minus 2 of Z mod P to the n is 0. 0. And that's what we call even vanishing. And we have explicit bounds, but let me not get into them right now, I'll get into them in a second. Okay, so that's what we call the even vanishing theorem. So again, this in particular implies, since we have the formula on the right hand side, we can say something about the order. So in this case, we know that the order of K2i minus 1 P p to the n is actually, let me maybe give you the order of the full group, so it's p to the I times n minus 1, and then I also multiply with the prime to p part, which is p to the I minus 1. Okay, so you can completely determine the orders of these groups in this regime where we have the even vanishing. And in fact, actually, this is kind of already very satisfying. You know the orders, but then you also want to know what the groups actually are, and you also want to know what happens in the regime in between the low degrees where you have even vanishing and the high degrees where even vanishing kicks in. I mean, there is this regime where provably by Nikolaus result even vanishing is false. And in fact, we also prove something about that, namely the following: there exists an explicit cochain complex of the following form for every fixed I and n. So there's an explicit cochain complex, which is cochain complex over the p-adix, I n minus 1. So it's a free module over the p-adix of rank I n minus 1. And I have a map to Zp to I n minus 1, and then again a free guy of this sort, I n minus 1, such that following holds h0 of this guy, I mean I'm writing it cohomological, so this is degree 0, I guess 1 cohomological minus 1 homological. So h0 is 0. H1 of this cochain complex is actually K2I minus 1 of Z mod p to the n p infinity torsion, and H2 is K2I minus 2 p infinity torsion. Right. And I guess, what does this mean? Explicit. So what's the meaning of the statement? So what I mean is, first of all, given such a cochain complex just means you have to give the differential. That means we just give a formula for two big matrices, right? And these formulas are kind of involved in inductive, but it's very explicit. It's so explicit that in fact you can feed this into a computer. So we wrote a Sage program, and this Sage program spits out for us all these K groups. Like, I guess at the moment we ran it until something like, at the prime 2 until something like the 50th K group. So we just produce tables at higher primes. Can also run it this far, but then it becomes less and less interesting because at some point, everything has been calculated by Nikolaus already. So at the prime 2, where only K0, 1, and 2 were computed, this is most interesting for something like Z mod 32 and so on and so forth.
You may have said this already, but how large is the I?
Yes, so the I is, I can give you let me give you a formula in a second, okay? So I give you an explicit formula in a second. Let me just say that in fact the logic is that we first found this part, then we wrote this computer program, and then we had these tables where all the zeros came up. And then we were like, this can't be random. And then somehow, we called it the even vanishing conjecture for 1 week. And then once you know what you're looking for, you have an explicit chain complex, you just want to prove that a certain group vanishes, right? H2. So then it's actually not that hard once you know what you're looking for to prove this. Okay, so that's the result. And now let me give you 2 remarks. So the first remark is that this is way more general. So everything works for OK mod m to the n, where K is a finite extension of QP. So a p-adic number field. So this simultaneously generalizes the case Z mod p to the n and the case fpx mod x to the n. So, and in fact, all the results up there are also true. So for example, this quotient statement, sufficiently interpreted, is also true in this generality.
So you mean this works for every global field, local field? Because
p-adic number field.
How do you generalize fpx mod x to the n? You want also function fields, right? No,
like you can do something like Zp x modulo. We're quotienting by power of the maximal ideal, right? So when you quotient by the maximal ideal, you can do something like.
Not a finite extension.
Yes, z x to the e minus p, where e is sufficiently large. And then the maximal ideal in that will be generated by x, and once you quotient by power of x, you also quotient by p if the e is larger than the power.
Okay.
And then, so the quotient is in fact also. And there's actually one fun thing about this. Okay, so maybe I can say something fun now that I wrote down this example. Because, okay, now let me give you the bound for even vanishing that Wolfgang asked about. So here's the bound. So the actual bound is that I has to be larger or equal p squared over p minus 1 squared times, and now we have p to the n over e minus 1. So what is e? E is the ramification index. And so in this case, up there the ramification index is 1. So you get the same thing. But here you see one fun thing. Because, I mean, the thing I strategically, stupidly now erased here actually tells you that you can write fpx mod x to the n as a quotient with arbitrarily high ramification. And because this vanishing is like anti-proportional, I mean, the e comes up in the denominator, you see somehow the even vanishing can be pushed arbitrarily low. So from this fact, you see that you have even vanishing in the left column in all degrees. Because, I mean, this is kind of, in some sense, I guess Achim keeps saying this is infinitely ramified. In some sense, you can write it as a quotient but with arbitrarily high ramification, and that's why somehow in the left column you have even vanishing, and in the right column you just can't do that, and that's why you have this bound for convention. Okay, right. This is very good. Okay,
but
good.
This is the one out in the optimum. Because you said the actual bound is this, but this is the bound you have, or do you know?
I mean, so yeah, so. I mean, this can probably be improved, so I think we didn't really push super hard. So what I think is like, for sure, is that it's gonna grow exponentially in p to the n over e. So what's the correct thing to say? The Landau class of that will be like p to the n over e, and then there's some multiplication with some constant and some additive constants. But somehow from the tables, I mean, you can sort of, from the tables we've produced, you can see this is not optimal, but sort of it grows exponentially, and also if you see like what the process is that makes this happen, it's very clear that it's going to be exponential. So, but probably with enough effort you can always like improve the constants in every single case a lot. Yes. Okay, good. So are there questions? Okay, then I mean, you know, I guess fortunately Christian has already told us how to approach such things, and I mean the way we do this is using phrase methods. So let me just give you like a very sketchy picture of what this means. I mean the first thing is, I mean immediately we know that if we want to compute something like categorical z mod p to the n, and you look at this p infinity torsion, and actually maybe the cleaner thing here to do would be to p complete, but that ends up being the same thing. We're talking about finite groups. And then this is actually isomorphic to Tc star, z mod p to the n, by, I guess, understood William McCarthy. So immediately here we can translate everything into a statement about Tc, and that's what we're going to do. Like, I guess I should say star larger than 0. And so we're really proving something about Tc. And second thing.
So you no need torsion there? Or?
Yes. Yes, no torsion there. Because it is already p complete. So as I said, like a priori, you see this guy is actually p complete.
Yeah.
And yeah, if you write p completion here, maybe you would believe it, but then okay, a posteriori you also see the right hand side is p power torsion. Yes, absolutely. And then of course, I mean, once you want to calculate Tc, as Christian has explained to us, we have this fiber sequence. Let me maybe say this for an arbitrary ring. We have this fiber sequence, Tc minus, and then we have Tp. And here's can minus phi. And I guess in general for a ring I would have to sort of complete here, but since our ring itself is p complete, this is not necessary. So I don't even need to mumble something like everything is implicitly p complete, because it's actually just is p complete. I don't need to p complete anything. Okay, so that's a fiber sequence that exists. And maybe the third thing that was recently discovered is that you have a filtration on this fiber sequence. So that's the work of Bhatt-Scholze. And then they say there's a filtration on this, and by this I mean this fiber sequence. I will say what this means in a second. I just mean there's a filtration. All these spectra have canonical filtrations compatible with all these maps. And let me say a bit more about this Bhatt-Scholze filtration. Before I say something, well, I want to say now what the associated graded is. Let me just say, like, this works for commutative rings, but in an amazing recent work by Hahn, Wilson, Ruxit, we have learned that this in fact works for R being an infinity ring. That's kind of the even filtration. I will not explore this. I will only talk about actual rings here, actual commutative rings. I just want to say that it turns out that there has been another kind of revolution on that end, like recently. Okay, so there's a filtration on this situation with associated graded. Graded starts looking like the following. So the filtration, the graded of the filtration on TC is called ZPIR. So that's the ice associated graded, and that's what is called symptomic cohomology. So basically this is a definition of symptomic cohomology, that you construct a filtration and call the associated graded symptomic cohomology. And then on the last term, the filter, the associated graded of the filter is something like Nygaard completed and Breuer-Kissing twisted prismatic cohomology. And the filtration here is I guess the ice piece of the Nygaard filtration. Oh, sorry. Okay, so that is a version of prismatic cohomology. So if you ignore these kind of funky sort of modifiers, this is just what is called prismatic cohomology, and this is what I will talk about for the rest of the talk. So there is the thing called prismatic cohomology, which is basically a spectrum associated to any ring. And then this comes with a filtration, and this is a piece in this filtration. And it comes with a map from here to there, which is phi minus cum. And then the fiber by definition is what is called symptomic cohomology these days. And somehow, I guess all of these are a priori associated gradients of a spectrum. So these are spectra, but it turns out these are actually chain complexes. So objects of DZ, the derived category of the integers. So that's, yeah, just by construction they end up being chain complexes. And let me just say another way of saying that is that there's a spectral sequence converging from the ice cohomology of this chain complex VPIR and converging to TC to I minus J of R. So that's just another way of saying there's a complete filtration, there's a conditionally convergent spectral sequence, and in reality I need to assume something about the ring for this to be true. It's P quasi LCI or quasi symptomic. One thing I want to mention though is that the reason this is useful, and this is what I will talk about now, is that somehow, while this was initially defined as the associated graded on something topological, now we have a completely algebraic sort of description of all these terms. And that's what makes this useful, right? Because somehow we want to compute topology, but sort of once we have a completely algebraic description which lets us get our hands on these objects, can sort of run this backwards and compute stuff. That's what kind of the amazing fact here. And let me just say, the last thing how this works out in the case of interest, so R equals Z mod P to the N, then this prismatic cohomology, and I guess I need to Nygaard complete and Breuer-Kissing twist, but it turns out you can, if you want, ignore this in this case, because it's automatic, is concentrated in degree -1. So it's a chain complex, but it's concentrated, has homology only in degree -1, homological degree -1. So as a result, we get that this guy, ZPI, R, is concentrated in degree in -1 and -2. Right, it's a fiber between two things which are concentrated in degree -1. So I guess I should have said not only is this object concentrated in -1, but all the filtration pieces also. And though this is concentrated in degree -1 and -2, and what does this mean? Let me just say this in words. This means the spectral sequence immediately collapses. There's just no space for differentials, and the cohomology groups, the homotopy groups of TC now, are actually just given by the cohomology of this like short chain complex. Right, these like two terms, this two-term chain complex, so to say. Right. And that's actually literally what our chain complex is. So our whole thing is just computing these objects very explicitly, and then reading off what the homotopy groups are. Okay, that's the spiel. Are there questions about that? Otherwise, I'll sort of spend the rest of my talk just talking about prismatic homology. And what this is and what kind of makes this whole thing tick. And so let me start about sort of delta rings and prisms. So this prismatic homology has been invented by Bhatt and Scholze, and
is that delta or?
Delta, that's supposed to be a delta. Yeah. I have not practiced for the last couple of days. Okay, so A is going to be a p-complete ring throughout. And let me first review what a delta ring is. So a ring homomorphism phi from A to A is called Frobenius list. If it is a Frobenius list. If phi of A is equal to A to the P for all mod P for all A. And equivalently, I can just say this diagrammatically. I take like a base change to Fp, and then I have two maps to A base change to Fp, namely the phi map and I guess the A to the P map, the Frobenius, and they have to be equal. And I don't like non-derived base changes. So what I want to do here is I want to derive this base change. So the thing is, if A has p torsion, then I want to replace this tensor product by a derived tensor product. And that results in the notion of a derived Frobenius list. So a derived Frobenius list. So the homomorphism is called a derived Frobenius list if the two maps A tensor derived tensor product, A tensor derived tensor product, same maps, phi and A to the P are homotopic. So there is a homotopy, are homotopic. And now I have to say homotopic as what? Because of course, I mean, this derived tensor product is a priori a chain complex, but it's more than that. It's actually a animated FP algebra, animated commutative FP algebra, aka a simplicial commutative FP algebra. And I want them to be homotopic as animated commutative FP algebras.
So homotopy not going to be part of the data?
Yes, so good question. So I guess I want to then say a delta ring is the triplet A, phi, and the homotopy H. So yes, the homotopy is.
What's the animated one? I don't know.
Okay, so I mean, you know what simplicial commutative FP algebras are? Yes, so it's a homotopy in the homotopy theory of simplicial commutative FP algebras. The reason, I mean, like, you know, you want to maybe, I mean, there's one category of simplicial commutative FP algebras and a localization at the quasi-isomorphs. And I want to sort of say a homotopy in the localized infinity category. To distinguish these two categories, somehow in recent years, people have started using this animated commutative terminology. Okay, so, and yeah, so very good question about whether or not this is part of the structure, and yes, it is. And you see, actually, you know, if you have an actual Frobenius lift, it might or might not be the case that you can extend it to a derived Frobenius lift, right? First of all, I mean, if you have a derived Frobenius lift, then on pi naught, you see, I mean, by passing to pi naught, you see that you have an actual Frobenius lift. But if you have a sort of ordinary Frobenius lift, it might not extend to a derived Frobenius lift, and even if it does, there might be different choices. So, okay. But anyway, so for us, this is not going to be super relevant, because if A is p torsion free, then this derived tensor product is just the same as the underived tensor product. And in that case, the notions actually agree. And for us, actually, all the examples we really care about will be p torsion free. So there's no difference.
So,
Yes?
is this the usual lettering with section to the truncated blah blah, or is it
What?
is it some derived version about lettering in the classical sense, or is it?
No, I mean, it's equivalent to the classical notion of a delta ring. So there is a sort of, okay, so maybe these delta rings are usually studied slightly differently. And they're also in homotopy theory sometimes called beta rings or beta p rings or lambda p rings. And the way you usually see that is that you have some sort of structure called delta. But the delta, if you unfold it, actually is just a different way of encoding this homotopy. So I like to say it this way because it's more conceptual and will carry over to the setting that I'm going to be in, well, I guess. How much time do I have?
You have another like at least 17 minutes. Maybe
17.
Maybe one minute more because I wasted your time with my joke.
10 minutes.
Okay, so
you have like 18 minutes.
okay, good. So let me give you two examples, or three actually maybe. So the first thing is like the p-adix. And what is how can I encode, I mean, how can I make the p-adix into a delta ring? Well, I guess now I have to give you a Frobenius lift. And I guess there is only one ring homomorphism from the p-adix to itself anyways, which is the identity. And this is the Frobenius lift, of course, right? Because mod p, the Frobenius is the identity. So that's the Frobenius lift. Now that's the first example, and this is, I mean, the initial delta ring. And I mean, another example that's relevant is Cp power 0c. And now I have to make a choice, and what I'm going to do is I'm going to say, like, let's define a Frobenius lift by sending z to the p. And of course, mod p by the Frobenius homomorphism, aka freshman stream, you know that somehow this is the same as taking a polynomial to the p's power, but integrally this is false. Right, okay, that's a delta ring. And let me first, as a last thing, maybe mention if k is any commutative ring. There's a thing called the Witt vectors of k, the p-typical Witt vectors. And that comes actually with a so-called Witt vector Frobenius. And that is a delta ring. And I'm actually skipping part of the datum here because those two examples were p-torsion free. But here it might happen that the p-typical Witt vectors are not p-torsion free. They are in most cases of practice. For example, if k is a perfect FP algebra, they are p-torsion free. Also, if k itself is p-torsion free. But for example, for rings like z mod p to the n or so, this will not be p-torsion free. And then I'm not giving you all the datum. One way to obtain this, though, is that you write this ring, I mean, you resolve this ring by p-torsion free ones, and there you have somehow Frobenius lift because it's p-torsion free, and then somehow you get a homotopy by exhibiting this diagram. Okay, so here you see really you need to sort of make sure you have this extra data. Okay, so what is a prism? A prism is a delta ring A together with an invertible ideal I. Right, so invertible ideal, sorry, A, that's the name for my ring. Invertible ideal just means invertible as an A model. Or equivalently, Zariski locally generated by a non-zero divisor.
No connection between I and delta, like I and phi, sorry.
Yes, so after erasing... sorry, yeah. Such that two conditions are satisfied? Such that the first condition is a rather technical condition that A is p comma I complete. And the second,
is derived become I complete or classically become I complete?
I mean, classically implies derived, so I guess if we're classically p comma I complete, we're fine. And if you press me really, what I want to do is I want to assume that p has, I mean, a mod I has bounded order of p token, then the two notions will agree. So that's like really what I'm really doing is actually in technical terms, I'm working with what is called a bounded prism, in which case you say a mod I has bounded order of p token. But I'm skipping this under the rug, so it's not incorrect what I'm saying because, as I say, like derived, I mean, actual complete implies derived complete. Okay, so this is one, and two is the prism condition, and this says that p is actually in I plus, sorry, I guess not direct, but plus phi I times A, I guess. That's the prism condition, and this is, I don't know, this is what it is. And it's kind of magic that this works, and I will try to convince you that it does now, but let me first sort of maybe draw the picture that we keep drawing for these prisms. So here's a picture. So I think of a prism as something two-dimensional, so that's spec A. A is a prism, and then here I'm having this kind of little prism thingy. This is spec A mod P. So the white light is the mod P reduction, and then I have these rays coming out. This is spec A mod I. And then the next thing is spec A mod phi I. And here you see the prism condition exactly means that these two lines intersect in the mod P reduction. That's literally what it means that P is in this intersection. And from this you can easily deduce that somehow the next thing is spec A mod phi squared I, and so on and so forth. That these all intersect in this guy. Okay, so that's maybe a picture of a prism. And versions of this picture, I guess there's also a cohomological picture, how the thing I'm going to define reduces to known cohomology theories. This is kind of why these things are called prisms.
Sorry, I don't understand. What do the lines to the spec? I know what spec is, but why do you draw lines? I don't know.
Well, if you have an ideal, if you have an ideal in a ring, then the quotient will be a closed subscheme of spec of that ring, right? Spec A mod I is a closed subset of spec A.
Okay.
And the way I think about it is that spec A is something two-dimensional and spec A mod I is something...
Spec A was on the line. Spec A is a whole plane.
No, yeah, spec A is the whole plane, sorry. Spec A is supposed to be two-dimensional and spec A mod I is this red line, spec A mod phi I is the yellow line, and so on and so forth. And spec A mod P is this kind of little prism there. Okay, now I'm going to give you a bunch of examples. First example is we take our delta ring to be Vp with the identity Frobenius above, then we can take the ideal to be the ideal generated by P. In which case the prism condition is trivially satisfied because P is already in the ideal, and that's the thing called the crystalline prism.
Thomas, stupid question, but I mean, P being in this ideal means they do intersect, right? Doesn't mean they don't intersect anywhere else.
Yes, I tried to indicate that they just intersect somewhere.
Okay.
As they don't, I mean, the intersection doesn't cover the whole like little prism thingy, right?
Okay.
Yes. Somehow, yeah, the picture, yeah.
Sure.
As good I had. Alright, okay, so that's a crystalline prism because somehow if I'm going to do prismatic cohomology, as I will define in a second, this will reduce to classical crystalline cohomology. The next example is ZPZ. And the ideal is now again a principal ideal. Fabian, can you maybe discuss this after the talk? Okay, so this is also a prism, and here actually it's less trivial to check that this satisfies the prism condition. So I guess, yeah, I leave that as an exercise to check. And this is called the Broglie-Kissing prism. Kissing prism. And maybe I give you one last example, and that's if, just for people who know what this means, if R is perfectoid, like integral perfectoid, something like, for example, think about Zp and adjoint p to the 1 over p infinity, something like that, then it turns out what you can define is something called A-inf of R, and that's just the bit vectors of the tilt, whatever the tilt is. And this comes with a canonical map. So I is going to be the kernel of the canonical map from A-inf R. This is a delta ring because it's bit vectors or something. As I said, like bit vectors are a delta ring, and this comes with a canonical map beta down to R. And I is the kernel of that. So that you see, you can recover the ring R as a quotient of the prism by its ideal.
So
And
so this thing is principal, and that is not sort of part of the, in some ways, like part of the data or something, or it's just like a special case.
you could ask. I don't think. It doesn't make sense. It's what do you mean?
No,
by,
what I mean is that, like, are there examples of
Yes.
are there examples of these reasons which are not of this form A?
Yes, there are examples, but even if, like in practice, most of the examples will be of the case where the ideal is generated by a non-zero divisor. But somehow, for the theory, it's important to allow general ideals, otherwise you can't.
And the first example is a special case, right?
The first example is a special case. So what I was going to say, if you don't know what a perfectoid ring is, actually it turned out this prism is perfect, meaning that the Frobenius is an isomorphism. And this assignment constitutes an equivalence of categories between perfect prisms and perfectoid rings. So if you don't know what perfectoid means, it's just a quotient of a perfect prism by its ideal. And that's kind of in general how prisms are a generalization of perfectoid rings, or deperfection, how they, Bhatt-Scholze called it in the paper, of perfectoid rings. Okay. Good, so now what's prismatic homology? So somehow, it's a huge mystery to me why this works, but this is, it's not a bad definition, right? It's not so complicated, it's just like completely mysterious why this is useful and plays any role. And here's how you use this to define prismatic homology. So what is prismatic homology? So R is going to be any p-complete ring. Complete ring. So first thing is I can define this prism R, this absolute prismatic homology that came up in my filtration of dp. And that's just going to be the limit over all maps from R to B mod J, where B, J is a prism, and then B. Then you take this limit, B is going to be a ring, so you consider it as an object in the derived category of the integers. And so you carry this limit out in the derived infinity category of the integers, so it's the homotopy limit. Okay, so that's the definition of prismatic homology, and that's due to Bhatt-Scholze, well, I don't know. And I guess it has recently, at the beginning of the year, this is kind of what's called absolute prismatic homology. This has extensively been studied by Bhatt-Scholze. And right, now here's a definition due to us, which is there's a relative version of absolute prismatic homology. And that is if A is a delta ring, base delta ring, and R is an A algebra. But R is just any algebra over A, not a delta ring or anything like that. Then what you can define is something called prism R relative A. And what you do here is you take a similar limit, somehow look at all, you have the situation where you have A maps down to R, and then again you want to approximate R by B mod J, where B is a prism, but now you also want to have a lift here. So that's supposed to be a map of delta rings. Delta ring map. Okay, I guess that's the definition which is due to us in this generality. And let me say a couple of words about what is going on here. So,
The brackets is actually indexing category, or?
yeah, so the indexing category is supposed to be this. Yeah, you're right. So I guess limit over this indexing category over B. Over B, sorry.
Okay.
Sorry, yeah. So this is supposed to be the indexing category, which I decided not to write under the limit operator. Okay, let me give you some intuition of what's going on. So let's imagine we have a topological space and we want to compute its cohomology. We know somehow under reasonability assumptions, cohomology is isomorphic to the Czech cohomology. How can we calculate Czech cohomology? What I can do is I can set up a site. I look at all contractible open sets of my space, and I look at the limit over all contractible open sets in my space over just the constant thing, the integers. Constant diagram the integers over every contractible open set. If I carry out this limit, what you get is a Czech cohomology. It's just one way of computing that. And here, this is kind of the way I consider it. So a map from R to B mod J is like a map from spec B mod J to spec R. So somehow the spec B mod J replaces my contractible open sets. So in this setting, somehow B mod J, I think of this as some sort of mill thickening of a contractible thing. B mod J is like the underlying thing, and B is kind of some internal structure to this contractible set. And then I take the limit of all possible ways of approximating my spec R by these kind of funky nilpotent points. That's kind of the way one can think about this prismatic cohomology. And here you do this also while working relative to some fixed base A. Okay, so let me make two remarks. First remark is, of course, that prism R is the same as prism R relative CP. So, like the relative one is a generalization of the absolute one. That's the first statement. And secondly, I should say a relative prismatic cohomology had been defined by Bhatt-Scholze before. They just were in the setup where A is itself a prism and R is an A mod I algebra. And then, I mean, it's our definition just reduced to theirs, but we just don't need A to be a prism itself. And actually what we need is, for in particular, this tells us that the initial definition of Bhatt-Scholze is more functorial than you a priori think. Namely, it's functorial in all delta ring maps in A. This is what we really need. And we somehow, it took us very long to realize that you can write down this definition. We first had this computational evidence that it's more functorial than you think, and yeah, eventually we came up with this very easy definition. And I guess I'm more or less out of time, right?
Ah, you have another 2 minutes.
2, oh,
Yeah.
very kind.
Pleasure.
Okay, so maybe then I wrap just up. Let me just say that I'm also slightly lying here. I mean, this side theoretic definition is only correct under the assumption that R is reasonable. In general, you need to take the non-abelian derived function of that. So this is only correct if R is P quasi LCI or P quasi atomic. For general rings, you can't extend this definition. But that's just a technicality. All our rings will be fine. Okay, so, and let me maybe sort of wrap up by saying how one computes this now. So the first thing is, if this site I write down, or this indexing category, for fixed A and R, has an initial object, then, well, of course, I mean, limit of a category which has an initial object will just be evaluation on that object. Then this prismatic cohomology, R relative A, is just this initial object B. It's just a triviality, but this turns out to happen a lot in practice. And this is actually the reason why we can compute stuff, or why Bhatt-Scholze sort of were able to compute stuff. So for example, if A is this guy, and R is Z mod P to the N, and with the map, I mean, to make R an A algebra, I have to tell you where to send Z. I'm going to send Z to P. In this case, you can compute what the prismatic cohomology is, and it turns out that Z mod P to the N relative this ZPZ, this prismatic cohomology, this ends up being just, I guess, ZPZ. And then you have to delta ring adjoin an element Z to the N over Z minus P. And complete that. And that means like adjoin such an element in the world of delta rings. is kind of a complicated process, but it's super explicit. That's why we can calculate stuff. And I guess, okay, let me say one last thing. And this is what we actually use in our calculation. And then finally, what you want to do is you want to compute the absolute prismatic homology of Pn. And then it turns out you can sort of use some descent statement from these relative ones. So what happens is that this chain complex, prismatic homology, z mod p to the n, this is somehow obtained as a totalization of a co-simplicial thing, where you first work relative to this one variable z, and then you can sort of work relative to variables, z mod p to the n, relative z, p brackets, z0, z1. And both of these variables go to the same element, p. And here it's important that this is not in a symmetric way in z0 and z1 a prism, but it's still in a canonical way a delta ring. And then you sort of have three variables and so on. And what happens is sort of, I mean, you prove that this is an equivalence. That's a descent statement. And then in order to compute this guy, you want to calculate those guys, but those are all discrete, just given by formulas of this sort. And then, I mean, the fun begins. And this is where my talk ends. What happens is actually you have to get explicit formulas when you prove this whole thing is actually, it's a co-simplicial thing, it's a one-dimensional Hopf-Algebraic. So what that means is you only have to compute these terms and the primitive elements here. And so the whole spectral sequence degenerates, and then you can give explicit formulas for those guys. And it ends up being the case that then this kind of three-term chain complex drops out of giving explicit generators for these guys. And I mean, I think the reason people hadn't been able to do that now is you have to do that in a way compatible with the Nygaard situation. That is like really complicated, but yeah, I guess with enough computer power and Achim and Ben attend, this was possible. Thank you.